Thank you, everybody, for joining us for another GraphGeeks talk. Today, we're going to talk about a meta learner that helps you find the best link prediction model for your specific data, which I find terribly exciting. So, my name is Amy Hotler. I'm the host, and we're joined today by two speakers, two researchers. The lead author on this research, Bisman Singh, is a data scientist. Recently earned his master's degree, congratulations, in computational and applied mathematics from the University of Colorado Boulder. And Bisman is very passionate about applying mathematical concepts and data science to solve actual problems, which is one of the things that I always appreciate about Aaron's work. So I've known Aaron Clauset, a professor at the University of Colorado Boulder, for quite a few years, and I've been following Aaron's work because he does tend to focus on things that are actually tangible things that we can use. So always appreciate that. And Aaron is an expert in network science and machine learning for complex systems. He is a recipient of the Erdős Renyi, if I'm saying that correctly, prize. So those network scientists in the crowd will understand how prestigious that is. And he also does a lot of algorithm work in community detection and link prediction as well. So with that, I will turn it over. Thank you again, Aaron and Bisman, for joining us today.
Today we're going to talk about meta-learning and link prediction. This is a paper that is on the archive now, and the way this will work is I'll speak for a little while, and then Bisman will take over and talk about the specific results from our paper, and then we'll switch again, and I'll wrap it up, and then we'll have a live demo of the Python package that we've developed with these techniques at the end. Okay, so what is link prediction? Well, networks are everywhere. I don't really need to sell the idea of networks being everywhere to this audience, but they represent all manner of interactions. So social connections, biological interactions, economic transactions, transportation links, etc. And so this data is increasingly a part of many both scientific and practical applications that we might be interested in. But there's a problem with most real-world network data, which is that it's incomplete because there are missing connections. Sometimes this is because of measurement, sometimes bias in the way we collect it, uncertainty, for instance, even on the social platforms. These days, we don't put all of our friendships on every platform. In fact, sometimes we sort of stratify our behavior across platforms. We'll use Instagram to connect with a different set of people than we use Snapchat or Facebook or whatever to connect with. And so inherently, network data that we might collect is missing information. So in the social networks, that's really because all of these networks are sampled. There are some edges that are hidden intentionally. For instance, some edges are unobservable because those interactions are simply invisible to those social networks, and some edges are future events, people you have not met yet or interacted with yet. In biological networks, most of these connections are observed by expensive experiments, typically paying a graduate student to do an experiment in the laboratory. And so edges have to be inferred from the little bit of data that we can get from these expensive experiments. In communication networks, as I mentioned, there's lots of off-platform interactions and different types of interactions. And so these missing connections are sort of a fact of life with all of the network data that we might be interested in. Link prediction helps us fill in those missing connections. It's useful for not just that task, but for many other things as well. For instance, you can compare different models. So if you have two models of a network and you want to know which one is better, you can ask which one predicts links more accurately that aren't observed. You can also use it for marshaling resources. If you're a field ecologist and you're going out into the field to observe a food web, for instance, you have limited time and energy. And so you might want to ask a model like, which connection should I try to sample next? Which are the most likely pairs of species to be interacting? That works just as well for CIA agents as it does for ecologists. And of course, you might want to predict future dynamics, which connections will form next. This is very much like some degree what the people you may know widget that we see in a lot of the social platforms is trying to do. So to give an example of what we mean by predicting these missing links, here's a network very easy to visualize from many years ago. It was collected after the fact of the 9/11 attacks. These are associations among 9/11 hijackers. The red, green, blue, and magenta nodes are specific hijackers known after the fact. And the cyan nodes are associates of theirs. And so suppose you were working in the intelligence industry and you wanted to know, like, well, which pairs of people are likely to have been interacting based on the pattern of the interactions I've seen in the full network. And so the goal is to take the observed network and then predict the actual network by filling in those missing links. Now, this problem is actually a very difficult problem. To give you some notation, let's just define the missing links, the true positives here, is the true edge set minus the observed edge set, so it's the difference between that. And for most networks, that's going to be something like big O of n, linear in the size of the system, because most real-world networks are sparse. And so when you remove a few edges from that, you also have a sparse set left over. The possible missing links, however, is a much larger set. So now we take all pairs of vertices and subtract off the things that we've observed, and that's the set of things we're trying to sift among to find the missing links. That set, because you're looking at all pairs of things, is order n squared. And so that implies that the baseline accuracy for guessing is 1 over n. This is a really hard problem. And as a result, when the networks get bigger and bigger and bigger, your chances of accurately guessing a missing link go down asymptotically. So this problem that we're going to try to solve is sort of general. There's lots of different versions of it. Recommendation algorithms are, in fact, a link prediction task. If you have a bipartite network, say you're Netflix and you're trying to predict which content you should recommend to users, you have your users on one side and your content on the other, and you're trying to predict links from the users to the content. So it's sort of a bipartite version of link prediction. One key difference with recommendation algorithms is that often you have rich node and edge attributes. So you know something about the content, like what kind of genre the movies are, and you know something about the users, what kinds of things they've interacted with before. And that makes it much easier because you have additional information other than just what they've interacted with. And another version of this problem is called matrix completion. This is where you have image or video and you're trying to do error correction. This one exploits the spatial correlations in the underlying system. But in networks, the general problem is to not have the spatial correlations or the edge or node metadata, and instead just have to learn from observing the connections alone which missing connections there might be. So we're not allowed to leverage node metadata or edge information. We just look at the binary adjacency matrix and try to guess where the missing links are. A technique that works well in this context likely will work better in the context where you have more information as well. Okay, now in practice, there are many thousands of link prediction methods. This is one of the more active areas of research and development in network science. But you can kind of cluster these thousands of different techniques into 3 large-scale families. And every one of these techniques has sort of the same basic structure in which you're trying to you develop a score function that takes as input a pair of nodes and output some real valued number. And then you can sort all the pairs and you say, well, the things that are at the top of that list that have high values, those are probably the missing links that we have. So the 3 main ways that we might do this are, one, we might use topological features. These are functions of node I and J's local neighborhood. So these are things like looking at the node degree. So if like 2 high degree nodes might be more likely to interact, or the number of common neighbors. If you're a social network, friends of a friend typically get introduced and become friends themselves. And so that triadic closure mechanism will tend to be a good way of predicting where missing links are. Shortest path, Jaccard coefficient, et cetera. These are topological functions, the very familiar summary statistics that we use in network science to describe the structure of a network. These things can be used for link prediction purposes as well. A second is to use sort of model-based methods, and these are functions of the entire graph now. If you're familiar with some of the Bayesian models in network science, these are like graphical models, stochastic block models, modularity, infomap, et cetera. These are models of the entire graph where they're trying to like decompose the structure of the network as a whole into some sort of smaller structures. And then you can use that information to try to predict where missing links may be. And the third popular method is embedding techniques. And so here we're going to learn sort of a vector representation of the graph where now each node is sort of located in some high dimensional vector space. And we want to put nodes that are connected in the observed graph close together in the vector space. So now this implies that if 2 nodes are close together in the vector space and are not connected, there's probably a missing link there. Now, the neural embeddings are really popular. You also have spectral techniques, graph neural networks, which we'll hear about later in the talk, node to vec, et cetera, et cetera. And across these different families of techniques, there's sort of 2 general ways that we might measure the accuracy. There's 2 use cases. The first is to use AUC, the area under the curve. This is a generic measure of class distinguishability. So can my machine learning technique learn to distinguish the true missing links from the non-missing links? So it's just a question of like, can I distinguish these 2 classes of things? The top K measure is more like I have a budget. So it's accuracy on a budget. I have so k guesses that I'm allowed to make, and I'm trying to maximize the number of true positives inside that budget. And these are both measures that we can use for binary classifiers. And as I said earlier, like we're just trying to predict whether you're missing or not missing. So that makes it a binary classification. There are, of course, other techniques you can use to measure accuracy like F1 and so on. But for this talk, we're going to focus on these two very popular ones because they sort of give you a general distinction between two different use cases. So in practice, looking at this massive literature of work from the past 20 years, most published link prediction methods work well. Every paper you read says like this method works well. Here's a table, my line is bolded and so on. But this raises some very interesting questions. Like, are they all learning the same thing? Is there one method that's best overall? Does how predictable links are vary across network types and settings? And are neural networks the best method to use? If you listen to most people who are sort of in the tech community space, like neural networks can solve all your problems. And I think it's a reasonable question to ask is, in this case, is that true? So let's tackle that first question of, is there a best link prediction method in general? And so we're going to do an all-to-all comparison. This is sort of the classic bake-off technique that you see in many of the papers, but we're going to make it a really systematic bake-off. We're going to try to compare all the methods against all the networks. So on the method side, we're going to develop 203 different features that we can write down for each pair of nodes that might be connected, I and J. 42 topological features. These are those summer statistics I mentioned. 11 of these network-based models, and 150 features from graph embeddings. And we're going to apply all 203 of those features to the data that comes from a very large corpus of networks, 550 structurally diverse networks that we developed from this website that I run, icon.colorado.edu. If you're looking for network data for examples and to play around with things, Icon is a great resource to use. So this corpus spans 6 different domains: social networks, biological networks, economic, technological, information, and transportation. And so it's going to give us sort of a generality to our results, because we can then see, like, are things easier in biological networks and economic networks, et cetera. So this is sort of a systematic bake-off type of approach. Our experiment here is, for each of these networks, we're going to hold out 20% of the edges, and that's going to be our cross-validation set. We're going to train a random forest over those 203 features on each of these subsampled graphs, and then we're going to ask a simple question: for what fraction of our corpus is a particular method the rth most important? So the random forest is going to allow us to sort of score how important these different features are for predicting the missing links. And what we find is that no method is really best or worst on all networks. You can see the dark red here in this sort of histogram plot. That's place where they, like many of the networks, the method is the best, or the rth best for many of the networks. And so where there's a lot of red density, that's where those techniques are doing really well. What you'll notice is that there's not sort of a universal dominance. And down here at the very bottom of the embedding dimensions, you'll notice these embedding distances. The dimensions themselves actually don't work very well, but when you start combining them, you start to get something that looks sort of competitive with the model-based and the topological base. But what's interesting about topological features, you can see on the other side, in the bottom ring, there's also some features that for some networks end up being sort of the worst. So this tells us that there's a lot of diversity in terms of how these different techniques actually work in practice on different networks. There's broad variability, and there's no method that's best or worst inside a single domain. So this tells us something really interesting and useful. It says that these methods make a diversity of errors. Right? The best method depends on the input itself. So whatever network you have, it might be that an embedding technique is going to work best on that, or it might be that topological measures work best on that particular network. This result also tells us that the methods are learning different things, and the performance varies really strongly across domains. But this is actually really great, because if the techniques are learning different signals, right, if there's a diversity of errors that we see here, then we can exploit that diversity using meta-learning in order to combine those different predictors and get something that's sort of strictly better than any one of the components. Now, in the modern methods for link prediction, graph neural networks are extremely popular. And so you sort of think that, like, yes, this is what graph neural networks are doing, is that the lower level of those neural networks are sort of integrating a lot of this different signal information together in order to produce something that's really, really good. So these graph neural networks, they learn these node embeddings by aggregating information from the neighbors. These GNN blocks are essentially using the input graph itself as the structure of the network at first. And one really nice thing is that GPUs accelerate a lot of things, and they can accelerate this process as well. So the generic sort of learning process here is I'm given a graph, often with some node features, although in this case we're going to ignore any node features in our graphs. We're going to apply this sort of stacked layers of graph convolutional networks or this graph sage algorithm to propagate the features. And then we're going to obtain those latent representations for two nodes that are unconnected, and then we're going to predict whether a link is there using some function. We contrast this with another very popular method, which is model stacking, which is a kind of meta-learning technique. And this is a direct method to average point estimates from multiple models, and this exploits the independence of errors. The learning process here is now you have to split your data into three sets. You have your holdout and then your test and train, because it's a supervised learning technique. We're going to fit and evaluate each sort of basic predictor, level 0 predictor as it's called in the lingo, on the same training test split. And then we're going to learn a prediction weight vector that minimizes the error on the holdout. And this has been shown to essentially construct an optimal predictive distribution over data. What's kind of interesting is this is a non-Bayesian technique, and it can be more accurate when the true data generating model is unknown. So it's good for working with real data, essentially. So we're going to ask a question, which is for link prediction itself, which is better in practice, graph neural networks or model stacking? And just as we did a moment ago, we're going to use our 550 network corpus. We're going to use AUC and top K metrics to evaluate these things. And we're going to ask the question of, well, can we even predict how accurate any particular algorithm might be in practice? So now I'm going to turn it over to Bisman, who's going to take you through those results.
Wonderful. And as we're switching over to Bisman, I'm just wondering, Aaron and Business, if you can also tell us what your motivation was to actually do this research. Were you looking for the best method, or were you just kind of evaluating things in general?
That's a great question. So our initial motivation was we've worked previously on the stacking techniques, and so we have direct experience with how well those do. But the stacking model is a two-level model. So you have your level 0 predictors, and then you have your level 1 predictor. And your level 1 model is a supervised model, and so we went into the project thinking like, well, how do we get different results depending on how we swap out that level 1 predictor? And could we put a neural network up there and try to leverage the advantages that people have been figuring out about how good these neural network techniques are? And so that led us down this path of doing this sort of very deep comparison of these advanced techniques to understand how can we squeeze out the most accuracy possible in a practical setting where you have a network in hand that you want to make predictions on.
So I'll continue from here. Basically, the first question that arises is that how well do different algorithms perform on each network? So this is our first experiment where we will compare different stacking approaches with neural net approaches. We will use a standard set of machine learning algorithms such as random forest, XGBoost, logistical regression, and support vector machines. Then we will compare them with two GNN techniques that we have, which are graph convolution network and graph sage, which is designed to be a bit better at most of the tasks that GNN performs. We will apply these methods to our corpus of 550 networks and simply ask, for each of our metric, which is AUC and top K, how often is a method the best, or within the 3% of the best across all networks. Here, I have organized the networks into 6 domains. Within each domain, there's a row of pixels, and each pixel represents the performance of an algorithm on a network. If a pixel is dark blue, that algorithm was the best for that particular network. And if the pixel was light blue, that algorithm was within 3% of the best. So when we apply all algorithms to our networks under these two metrics, we get the following visualization. So what we see here is a huge amount of diversity, just as we expected from our previous results. Which algorithm is really best depends on the network. Still, we do see some very interesting patterns here. Almost all algorithms under both of our metric perform very well on social networks. Essentially, almost every algorithm is under 3% of the best on these networks. Among the social networks, which are relatively easy to predict, for AUC, random forest, and XGBoost are generally the best, although GNNs are also quite close here. For prediction in budget measured by top K accuracy, it's not random forest or XGBoost. that performance is best for logistic regression. So basically, again, most of our algorithms also perform reasonably well. But what happens when we look beyond our social networks? We find that each algorithm show a large amount of variance in performance. Random forests, for example, are very accurate for AUC across domains. But within each domain, there are plenty of cases where random forests are not even within the 3% or the best algorithm. We see this repeated pattern across all techniques. Essentially, what I'm trying to say here, it really depends on the particular network you're using, which network performs the best. So at the end, social networks, the takeaways here are social networks are relatively easy for link prediction. And we'll see why this is the case in a moment. Random forests with stacking perform very well on AUC. Although on the contrary, in top K, graph convolution networks perform quite well on top K accuracy. So this raises a natural questions for us. What feature of a network explain these differences in the performance?
In
moving
Bisman, as you're moving forward, I've just got to say, wow. The variability here is really impressive. And as somebody who is not a researcher, but a practitioner, it can be very frustrating to read through research and, see really high, either AUC or top K. It's really high, the bold line, as Aaron said, of, here's the proof that ours is the best. And then to look at this, in my mind, I'm like, okay, well, if you cherry pick, if you select a network that does really well with your new algorithm or your new method, you're going to get great results, but that doesn't necessarily mean that it's going to work well on my data.
So the question we are trying to ask is, are there any features which have some correlation with the topological features, and do accuracies such as AUC and the top K, are those two metrics correlate with the topological features? So what we do here, as you can see, is we have AUC on the top row and top K on the bottom row. Each line represents one link predictor. So basically, stack model with random forest stacking with logistic regression, DCNs, and SAGE, showing how its accuracy changes with the network's feature. For example, on the left hand, you see for average degree, generally all algorithms achieve better link prediction accuracy when the average degree is higher, meaning like there are more connections to learn from. But on the other hand, if you see on the right hand, similar trend also persists. For example, as triangles or clustering coefficient increases, accuracy also tends to perform better. But if we also see some diversity among different techniques, on AUC we can see there are separation between algorithms. Even we see that in clustering coefficient. Also to note here is that when degree assortativity becomes more positive, meaning nodes with similar degrees are more likely to connect, accuracy also to increase. So this gives us the evidence that topological features do tend to matter when we are doing link prediction. And of course, these statistics are very wide across different networks. So now the question that arises is, and since we know that these features matter, the next step we can ask is, can we actually learn which methods to use based on these features? So for that, what we do here is we leverage error diversity. Different methods learn different things. We simply regress our performance metric, which is top K and AUC, on the network's descriptive statistics. For each network, we record statistics such as clustering coefficient, variance of degree, and average degree, and more, as you can see on the slide. Then we ask, can a model learn to map these statistics to algorithm accuracy? Basically, can we have a function which takes this descriptive statistics as an input and spits out the top K and the AUC for our network, which can give us some kind of bound to estimate what is our top K and AUC. And as we see here, we can see there is a significant importance of certain features. And what we see here, if we look at the metric AUC, the variance of the degree distribution and clustering coefficient are really predictive. But on the other hand, if we see top K, then average degree is really predictive. So what we indeed see here is that network structure can predict algorithm accuracy. But we don't stop here. We go one step more, because the real challenge is, can we automatically pick the best algorithm on a given network? So for that, we wanted to test that hypothesis. We train a random forest to predict which method will be the best from network's descriptive statistics. In the end, we don't want to run every algorithm on every network. Instead, we want to ask, tell me the algorithm which I should run as a practitioner, as a researcher, based on my network's feature. We then compare two models. So we have model one, which includes all of the 6 algorithms that we've mentioned previously, and model two, which has random forest and graph sage, because those were leading candidates in our study. Then we compare each of the meta-learning model to the Oracle. Oracle runs all the model and always picks the best one, gives us an upper bound on the performance. So basically, Oracle is the ground truth coming from our data. So the gap between Oracle and our learned model shows how much the accuracy we lose by having to learn the function. So we can proceed further and see how does our Oracle do and how does our models do. So what we see here for AUC, we find that Meta Learner Model 1 outperforms the baseline, and baseline here being Graph Sage. Like if we are using only Graph Sage on our corpus, what is the average AUC that we get? And similarly for Graph Sage as well. And if we see the Model 2, which we have only Random Forest and Sage, it learns when Random Forest or Sage fails and knows which one to pick. That's why it's higher than the baselines. But as we see, learning is not perfect. There's still a small gap between the Oracle's performance and the performance of our learned models. That's for AUC. Now we can move on to the top K and see what are the results. So for top K, the model that chooses among all the 6 outperforms the baseline model. However, there's still a small gap compared to the Oracle. If we restrict the choice only to random forest of graph sage, it's harder to beat the baseline. That's because for top K, one of the model is almost best for top K. So for example, here graph sage outperforms random forest in almost every cases. And that's why we have this, the lines coincide. So overall, Meta Learner works, but its success depends on the metric and the diversity of models available. So now I will give the slides to Aaron, and he can continue with the conclusions.
So I have a quick question again as we're switching screens. Bisman, did you find that it was completely network structure dependent, or was it network structure plus domain? So networks, does the domain, whether it's like transport or social, actually influence the outcome, or is it just because the network structure of that domain was one way or the other?
So we cannot say that domains and network structure are independent. For example, in social networks, the average degree and clustering coefficient is much more higher than economic networks or biological networks. So we cannot say that domain is independent of your edge of your network structure, but yes, both of them matter in our accuracy.
All right, thanks.
Good. Okay, so let's wrap up here. What have we learned? Well, as we argued in the very beginning, link prediction is a general task in network science. It's sort of useful for many different things. And it's because all networks are incomplete in some way. So link prediction helps fill in those missing edges, or the ones that you want to predict in the future. And we found pretty conclusively that there's no link predictor that's best on all networks. This is a little bit like a no free lunch theorem in machine learning, if you're familiar with that theoretical result. And link prediction algorithms make a diversity of errors. They're not all trying to learn or predict on the same signals. And that's really great because it offers an opportunity to use meta-learning, particularly stacking, as a solution. So model stacking allows us to achieve sort of nearly optimal predictions by combining many different predictors. And as we showed, you can take things like graph neural networks and put them inside your model stacking and leverage whatever those signals, those techniques learn. We also found that social networks are just kind of the easy mode of link prediction, and largely that's because they have a higher average degree and high clustering. So there's lots of information to learn from in a social network, which is different from things like economic networks and technological networks, which are lower average degree and less clustering coefficients, for instance. We find that predictions on a budget, which is the top K prediction, is generally harder than distinguishing classes. So even if a technique is good at telling missing links from non-missing links, if you're only making predictions for the top 100 cases, for instance, like you're putting things in a carousel for recommendations, then that's actually a much harder problem because you have to be able to get a certain number of true positives in that top set. But we find that model stacking in this meta-learning approach is a really smart way of leveraging all the available techniques. And it's generally as fast as GNNs. Model stacking doesn't require GPUs to run, and it has similar accuracy. So it's a pretty great result in the sense that if you don't have a big budget to spend on GPUs, you don't have to. You can still get really great results using the model stacking approach. And we can show that you can learn how to predict which algorithm will do best on your particular network, given the features that you can calculate on it, without having to run any algorithms on it in order to assess that question. So we have a preprint online. Here's the archive indicator for it. Meta-learning optimizes predictions of missing links in real-world networks. I want to thank our co-author, Lucy Van Kloon, who couldn't be here today. And now I'm going to turn it back over to Bisman, who's going to give us a live demo of how to use the package. And I think then we can wrap up and take some questions.
So now I will cover our link prediction demo. So we created this package so that practitioners and users, researchers can easily use our package. So our goal here was to have a package which is very easy to use, like a simple API that can do your data set preparation, that can evaluate your models and give you the metrics. It's highly configurable. That means that you can adjust your fractions, how you're sampling, the number of features you want to use, the number of cross-validation folds that you want to use can be easily adjustable by just fixing certain parameters. We do support multiple models. So the classical machine learning models such as random forest, XGBoost, logistic regression, and also in GNNs we support GCNs and SAGE. We aim for a structured evaluation, that meaning that we want to test these models or any model that you may want to introduce in future in a principled way through well-defined scenarios. And now I'll come to the interesting part of our research, which is a meta-learner. So what we did was, as we saw in the slides, that we trained a random forest to predict on the basis of high-level graph statistics such as clustering coefficient, assortivity, and etc., to predict which is the best model if our concerned metrics is AUC or top K accuracy. And it also helps us to give us expected AUC and top K accuracy on a given network. So this helps practitioners to avoid exhaustive research. So you don't have to go through the brute force way of looking through every models, calculating the metrics, and then comparing all the models. So you can just go to the model that this package provides. So now I will go through certain scenarios which I have mentioned in my package, and you can easily use them by changing certain parameters. So there are three scenarios that we have in our package. The first one is simulation. So what we do here is we randomly hide some edges to create a partially observed graph. Then train a model on this incomplete graph and test whether we can recover the missing edges or not. This is very useful for us when we are benchmarking algorithms under controlled and train and test splits. So basically, if you introduce a new model or a new network, you want to test that and benchmark that, you can use this package. So the next scenario that we have is specific links. What this specific links does is the user provides us a set of candidates or node pairs, and then we observe the graph and generate the prediction only for those particular pairs. For example, you want to have a hypothesis-driven question like, will protein A interact with protein B? This is a really good scenario to use when you're doing predictions on a budget or under data constraints, that you want to only focus on certain edges, not the whole sample of negative edges. And by negative edges, I mean non-edge pairs. So in the end, we have this another scenario, which is called discovery. So we will consider all non-edges. So on a given graph, we can have a lot of non-existing edges, which can be an edge in the future. What we do is we rank them by the likelihood of forming a link in the future, and then we try to predict what would be the accuracy for that. And this is very useful when we want to uncover like novel connections, such as new friends, new drug interactions, etc. So today we will cover certain scenarios in our demo. For the sake of time, we will go through simulation and specific links. We will not go through the discovery one, but I have given the GitHub link. People can go there, and I have provided a collab notebook there. People can run that notebook or download this package to play around with this. So now I will go through my demo, and for that I need to load some of my packages. So I did that. Now we will consider a basic social network, which is called Norwegian Board of Directors. So I'll run that just to give you a quick visualization of the network. So what we see here is we have 852 nodes and around 2,500, 2,700 edges, where each node represents a board of director. This is a very common social network and used in a lot of benchmarking studies as well. And each of the edges here tells you when the two directors sit on the same board. So again, it's a social network, and we can see this pretty graph here. We will move on to prepare our data set for link prediction. So currently we are focusing on our simulation scenario. Just to recap, what we will do here, we will take out certain observed edges. That means, let's say we are using 2,700 edges. We will take out 80% of the edges to train our graph, while the 20% of the edges are there for our prediction. We will also add certain non-existing pairs so that we can give you a correct AUC or top K scores. So can we classify the true links against the non-existing links or node pairs? One important thing to note here is that our package is highly configurable. So as you can see in the screen, I have observed fraction, training fraction, and false, train negative samples. So these are just some parameters that you can use to prepare your own data set. So for example, here I'm using 80% of the edges to observe the graph, on the basis of which I will make my predictions. I'm using 80% of the edges to train my graph. I'm using 3 cross folds, and I'm introducing 10,000 non-edge pairs. So what I will do is I will run my data preparation code. And what you see here, what we do is we hid edges, train on remaining, trying to recover hidden ones. And the configuration is hide 20% edges for testing. So it gives you certain information. Now we will move on to training our stacked models. So I'll run the slide, and then I can tell you more about this. While it is training, like our models are training, I use 2 models called Random Forest and XGBoost. For the sake of time, I'm not using logistic regression or SVC, but people can go to my collab and they can run SVNs and logistic regression as well. We evaluate these models on the basis of ROC AUC score and top K, where K is 100. So basically this meaning how many of the true links appear in the top 100 predictions given by our models. We also note the training time to understand the efficiency. So now we have trained our link prediction model. Just so that people understand, we have 20,000 training examples here, because we are using some kind of oversampling. We have 10,000 negative edges, and we have certain positive edges, but we have oversampled to balance the training. But as you see in the test samples, we have 10,000 non-existing pairs and 560 positive edges. So our goal is we want to classify those 10,000 edges as non-existing links and 560 as positive existing links. So moving on, I'll report the AUC and scores after I train my GNN model so that we can have a comparative analysis. So I'll run my GNN model right now. For GNN models as well, we have 2 models that we have introduced, which is the GCN and SAGE. We also offer to cross-validate GNNs. It's very difficult to work with GNNs, and how do we start and where do we start? So this package allows people to just use GCNs in a very cohesive manner. We also give you a cross-validation strategy so that you can understand what kind of learning rates you should use or dropout ratios you should use. We also give you epochs, how much you want to train your model. But also we introduce early stopping here so that our model doesn't overtrain. So now as we see our GNN model has been trained, we can compare these results. So what we see here that random forest and XGBoost perform really close. In fact, for top K, they are the same. But we see GNNs don't perform that well on this network. And that's a big thing if we see that. Also, if you look at the training time, random forest takes around 8 seconds, XGBoost takes around 2 seconds, and GNN take around 15 seconds. So the training time does depend on how many cross-validation folds you are using, or are you doing on a CPU or a GPU. But generally, if you want just fast results and you don't have the access to high computing GPUs, use random forest or XGBoost. Those are really fast. So now we will go and use the best part of our paper, which is the meta learner. Can we predict, as we see here, can our model predict either the random forest or XGBoost for ROC and top K? Because those metrics perform really close. Can we predict one of them? And note, in our model, it can also give us logistic regression, SVM, Singh. So we will see that. So what this model will give us, till the time I'm training this model, it will give us which machine learning network or GNNs will give us the best ROC, which one will give us the best top K, and what would be our expected ROC and top K. So I will give you a visualization and let's see. So you see here that the actual best models for random forest and for top K and ROC, we can argue both were really close for actual best model. XGBoost were performing the same. But we also do see the predicted models were like XGBoost AUC and our random forest top K, and the accuracies are pretty close. Like the expected scores are pretty close. So the good thing is our model did not choose GNN, Sage, or other models, and we are able to see what the bound that the score has given to us is really close to actual score. So this helps a lot of users to not go through the brute force algorithm of I'll check this model out and I'll check that model out and I'll go through thousands of hours of training and using my compute power. So you can use this model, see what is the expected score, and use the models recommended by our meta learner. So this was our simulation scenario where we hide some edges to uncover those hidden edges. Now we will go to our specific link scenario. So for that, I'll just load a simple network, the Karate Club network. A lot of practitioners use this network for their benchmarking studies. It's a simple network with 34 nodes and 76 edges, where each node is a club member and the edge is the friendship between them. So now we will prepare the data set for specific link prediction. So here we provide our own candidates. We want to see for node 0, who are friends with node 0, who can be friends with node 0. So what we do is we take the non-existing edge pairs with node 0. So can node 0 be, or the member 0 can be friends with member 17, member 18, and so on, member 33. Then what we do is we prepare the observed and training graphs. All of this is done in the model with few lines of code. You can do this. Sample negative edges for balance, train a model, and output the prediction score. So as you see here, our model gave some, but I will not gonna we can see more visually in a better manner. So I'll run a visualization. But just one thing to note here is that it gave us scores on those edges that we provided. So we wanted to provide who can be friends with node 0. So I'll just run a basic visualization so that we can see. So what this visualization tells us that, hey, there are some high likelihood edge pairs that our model scored. For example, here with 0 and 19, 0 and 30, 0 and 32, there's a big possibility that they can be friends. There's a medium likelihood that pairs like 0 and 5, 0 and 22 might not be that friends. And there's some low likelihood. Well, this was for ease of visualization. Our model basically gives you a score for your given candidates. This is really good when you're doing some targeted research and you want to do your prediction under certain constraints or budget. One thing we note here is that we did some very small our demo on very small networks, but we can we can run our package on like 40,000, 50,000 nodes as we did on our paper. So you can scale this to a higher dimension of the network. So that was our demo. People can check out my GitHub link if they want to play around the model. They can download this package. We can take some questions now.
Please go ahead and either raise your hand if you want to speak a question or drop it in the chat. But while we kind of prepare for that or people think about their questions, I'm wondering if somebody wanted to just get started, what would you recommend they do first? Do you have any tips that you learned, developing this?
So specifically mean prediction, if people want to get started here, is basically, first of all, understand your network. Like what is the characteristic of your network? Just do a basic summary statistics. But if they want to do link prediction, what they can do is they have to understand, like, okay, how do I prepare my data? And our model provides that, how they should prepare our data. Because I think the most important part, even regardless of modeling, is how do you prepare your data? That's something that is very important. And then you can use some basic techniques like random forest. You don't even have to go to GNN and GCN if you're not doing like high computation level or like prediction. But our package is really like scalable, so you can do those. But I will suggest prepare your data, do some basic descriptive analysis, and then use the basic model like random forest to see how good of an edge it is. And for starting, I would say people should use the simulation scenario so that they can get comfortable with the whole working.
And I like how you showed that you can get fairly good results efficiently, cost efficiently, and then go from there depending on what your requirements are, which is always nice because many of us don't have access to as many GPUs as we would like. So that makes a lot of sense. Are there, as people think about playing around with this, are there certain domains? So going back to that that kind of thread of thought, are there certain domains where you would like to test more of that maybe you didn't have as much data, or as in those 550 networks you tested, maybe there are certain domains that were a little thinner than others? Are there certain areas you want more information on?
Sure, I would like to go through more of the economic and transaction networks, and also to be precise, I would like to test this on temporal networks. And I know Aaron has done his own research on temporal networks, but I would like to see, can we do this iteratively in temporal networks and see how does it do when we don't have the information on the third dimension, which is the time here.
Yeah, good point. I was going to also ask about future research, so that kind of hits into that area. In particular, financial networks are notoriously tricky and tricky to get data on. And since this is about filling in links that are either missing or we didn't collect or are suspect or particularly hidden, especially if you're talking about fraud, most fraudsters are trying to hide their tracks. The idea of that being an area to get more data on, but also of the temporal aspect in financial issues and financial crimes are just really important. So is that along the lines of where you're both thinking about future work?
So that's one thing. Aaron can add if he wants, but I'll just give like two, 3 lines on the future work, I would say. One is that also represents the online prediction. Can we just keep on updating our link prediction partner on an online setting rather than training everything more like a transfer learning setting? Also, I think that there's a lot of research areas in how we should sample our graphs to train them efficiently. The graphs should be connected. What should be the distribution of the nodes that you're sampling? Should we use high degree nodes to sample? That's one thing. And the third thing that I think is just using more topological features in GNNs and see how well do they perform. Because at the end of the day, they're also kind of stacking if you think about it. Can we do those? We use node features where we don't have right now. We don't have node features. Can we use topological features such as average degree or basically Jaccard coefficient, things like that? Those are edge features though in the GNN setting and predict links.
Okay, so it's a really interesting question because as we showed that in social networks, link prediction seems to be just easy, and it seems to be because there's just so much data to learn from. But also links are highly correlated with each other. The reason links are easy to predict is in part because triangles are sort of the main structural element of social networks. But in other kinds of networks, like economic networks, the fact that link prediction is much harder may indicate that we have sort of overfitted our link prediction techniques to social networks, the kinds of patterns that are there. And we've underexplored or under-enumerated the kinds of features that are useful for making predictions in these non-social networks. And I think that one of the really great things about the stacking technique is that it's extensible, right? You can throw in any other features that come up. If you have some basic theoretical knowledge of how financial fraud works, the kinds of topological features that the fraudsters like to construct in order to move money around, you can just design a feature, throw that in there, and the stacking model will take advantage of it to the extent that it can. In some sense, it's very much like the way we like to use regression for things, which is sort of a generic framework for doing learning with vector data. Stacking lets us do that with network data.
Excellent. The point about the fact that we may have all overfitted on social networks is a really interesting and in hindsight seems quite logical that would have happened. I do have a question about kind of predicting link types or edge types. So entity resolution, disambiguation, is extraction is a hot topic in the LLM world right now, and a lot of GraphRag that's going on. And it occurs to me we are not that evolved in the same kind of discipline for edges. So in general, there's a lot of different processes. There's some very good ones. There's some manual plus automatic processes for entity extraction and resolution. But it feels like in the edge space, that's just more nascent. And I'm wondering if some of what you're doing might be very helpful in not just link prediction, but predicting what type of link something is.
So I would say my hypothesis says that we can do, because at the end of the day, right now we are just doing a binary classification. What we're doing is, does this edge exist or not? The question there becomes, what is the association of this edge? Can we do a multi-class classification? I'm not stayed on with the fact that I'm saying it will be good, but I'm just saying that my hypothesis is that it's depending on the topological features, we can surely have a correlated function to classify certain edges into certain categories. So I think that can be extended. That's a good idea, though.
Very cool. So we only have a few minutes left, and I'd love to hear from both of you either a few parting thoughts you'd like the audience to remember, or something you're excited about working on next.
I think maybe I'll just say one sort of closing word to summarize things, which is that in the current sort of space of people working with link prediction and networks, the graph neural networks are just it's so loud. Everything is being thrown into neural networks, and the techniques are really, really cool. But I think it's useful to step back and remember that in practical settings, sometimes sort of simpler ends up being more robust to the kind of weirdnesses that are in your data. And also in this case, simpler is both faster and just as accurate. And so in some sense, it's not necessary to have like the fanciest, most powerful, most mathematically complicated tool with the most data needs and the most compute needs. Instead, you can get away with doing something thoughtful on a CPU that is just about sort of lightweight modeling like our stacking technique. So I think this is really exciting to me because it shows that link prediction isn't as computationally intensive as you really need, as you might have thought it was, and you can do a lot with a little.
Awesome. Great. But we like our shiny new tools, right?
Me too.
Yeah. Always the pragmatist there. So, Bisman, how about you?
So I think, like extending what Aaron has said, I think a lot of our energy is diverted into building new models, but I think we kind of discount on the foundational understanding of the data. So, for example, like even with random forest, can we just improve that with sampling our edges better? Can we sample our graph better? So, for example, like if you're doing just like we're sampling disconnected graphs, or can we sample on the basis of like high degree nodes or low degree nodes? So I think those kind of strategies and using simple strategies to accelerate and help the link prediction models would be better. And it's also like, can we like that is the foundational knowledge of networks. Can we go into the principle zero or level one thinking in our own model stacking mind? Can we go into the level one thinking and just try to improve that? So I think that would be my next goal, to see, okay, what are some foundational steps which we might be missing at the moment, and how can we improve that, rather than going into sophisticated high computational models.
Awesome. I love it. Very practical. Thank you both for joining us today and presenting this, what I feel is important research, because it has real world applicability that we can use today, which is always appreciated by our practitioners. Thank you for people who are joining us live, and then of course who will watch afterwards. We've included some links, and I'll do that in the recording as well, so that you can find the research and get a hold of both Bisman and Aaron afterwards. So thank you, everybody.